All right, we're almost done with statistics. These next couple of videos, today and tomorrow's, is mostly review of stuff we've done earlier in the year, kind of just putting everything together. So you pretty much know everything you need to know at this point. Anyways, take a look at this warm-up. Take a few minutes to, I'll read it through, and we'll see how it goes. Erin is comparing sample means from two groups of 20 students involved in a controlled experiment. Her sample means have a difference of 5.68. Erin uses simulation software to randomly assign 40 data values from the experiment to two groups and find their difference between their averages. After repeating this process 100 times, the differences between the sample means generated by the simulation software approximate a normal curve with an average difference of 0.4 and a standard deviation of 2.7. Now let's talk about what this is saying. There's two groups of 20, so 40 students total. Her specific grouping has a difference of 5.68. Then she's randomly taking these 40 students, two groups of 20, and assigning them to two different groups. So this is that whole comparing two groups things like we did in the last video. When they randomly assign them to two groups and calculate the difference, we'd expect their average to be about 0. And it says the average difference comes out to be 0.4. Repeating this process 100 times, there'd be 100 dots if you saw the distribution. And notice 0.4 and 2.7 are the mean and standard deviation of the sampling distribution. Okay. So now it says determine the margin of error for the simulation and a range of plausible values for the mean difference between the two randomly assigned groups. And then once you do that, tell me, do you think the difference Erin calculated, that 5.68, is statistically significant? So hit pause, see if you remember how to do this, and then I'll show you the answer. All right, ready to see it? Well, here we go. So again, this is the mean and standard deviation of the distribution. Okay, so the margin of error is always plus or minus 2 standard deviations of the sampling distribution, which is what that number is. So it's plus or minus 2 times 2.7. And if you do that, you'll get plus or minus 5.4. That's the margin of error. Now the range of plausible values is when we take the mean of the distribution, 0.4, plus or minus 2 standard deviations. Or in other words, mean plus or minus the margin of error. That means the same thing. So for us, it would be 0.4 plus or minus that 5.4 number. Okay, so 0.4 plus 5.4 is going to be 5.8. 0.4 minus 5.4, I think it's going to be negative 5, but let's double check. Yep. So the range of plausible values is anywhere between negative 5 and 5.8, a pretty big range. But now, do you think the difference Erin calculated was statistically significant? Her calculated difference was 5.68. Is that statistically significant? Not quite. Even though it seems large, it's still within the range of plausible values. It's near the upper end of this range, but it's there. So I would say no. And the reason is a difference of 5.68 is within the range of plausible values. And for your random fact, there are 7 letters that look the same upside down as right side up. My daughter's learning that right now. All right, so what we're doing today is we're taking a step back from sampling distributions and going back to regressions. And this is another thing that gets used in statistics a lot. We've done it throughout the year, but I wanted to do one day where we kind of put it all together. It says throughout Algebra 2, we've looked at several different function families, each of which have graphs with distinct shapes that can be used to model real-world phenomena. Choosing the most appropriate model given a set of data is very important so that we get the most accurate representation of the data we are given. That's called interpolation. And we can make the most likely predictions of what might happen in the future, extrapolation. And we've used those words all year too. Remember, if you're within a given set of data or without given data that we have, if you're making a prediction. So these are all the different function families we've done this year that we've done regressions with. The first was linear. And we all know linear looks like a straight line. So it could be increasing or decreasing, but regardless, that's a linear line. And according to the regression in your calculator, the general form is y equals ax plus b. And all these that I talk about, I think you know where they are, but you go to stat, calc, and there's all the regressions. So for us, it's linear regressions choice 4, linreg. Okay, quadratics, what does that look like? Right, a parabola. And those have the form y equals ax squared plus bx plus c. And that's choice 5 in that menu called quadreg. Cubics look like this, kind of like the snaky graphs. And those kind of are like quadratics, but they start with y equals ax to the third plus bx squared. I'm just going to say plus dot 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 because those go on down to a constant. And in that menu, that would be cubic reg. Quartics look like the M's or the W's. One of those look the same side, upside down or right side up. Like cubic, that starts with ax, but it's to the fourth now, plus bx cubed, etc. That's choice 7, which is called quartic reg, or quart reg, I think it is. Sorry, it's kind of small to write in here. Exponential graphs increase without bound, but they have an asymptote, a horizontal asymptote. Those are the ones that are y equals a times b to the x power. And in our list, that's choice 0, which is called exp for exponential reg. We briefly did logarithmics, which is just the inverse of an exponential. So instead of a horizontal asymptote, there's a vertical asymptote. And the graph grows initially fast, but then a little bit slower. The equation for that is y equals a plus b ln of x. And that's choice 9 in our list, called ln reg. Where ln was a special type of log. What was the base of an ln? E. And then sinusoidal graphs are the ones that go on and on forever. They're periodic. They can be sine or cosine. But we always use the sine graph. Y equals a sine of bx plus c plus d. And that is choice C in that list, which is sine reg. All right, so those are all the ones we've done this year. If you look at this list, there's actually a couple other ones. We did most of them, but there's another linear regression just written the other way. So I don't usually use 8, but technically 4 and 8 could both be used for linear regression. There's this thing called power regression, which we actually did talk about. It's kind of like polynomial, cubic or quartic. Logistic regression is an interesting one. That would look like an S. It kind of starts slow, grows fast, and then levels off. We're not talking about those types of graphs, but those are the types of graphs that you'd look at like for the increase of an infection. Initially, it's pretty slow, gets fast for a while, and then once most people get infected, it kind of levels off. We did sine reg. We've done most of them. just a couple we haven't talked about. So what we're going to do today is we're going to look at a lot of different ones, and I'm not going to tell you which type of regression it is. So the only really new piece is that you're going to have to make a scatter plot, which you've done before. We're going to have to look at what the shape of the data points are and decide which one would be the most appropriate one to use. All right, so here's how it's going to go. Based on tests made by the Bureau of Public Records, here are distances in feet it takes to stop in minimum time under emergency situations. So this is the speed you're going, this is how long you need in order to stop. Part A, create a scatter plot of this data using your graphing calculator. Use it to determine what type of function could be used to model this situation. All right, so the first thing we got to do is we got to put speed into L1, stopping distance into L2. So stat, edit, clear out anything you got in there. We got an L1, 10, 20, 30, 40, 50, 60, 70. I'll go over to L2 and type in the stopping distances. Looks like it's 19, 42, 73, 116, 173, 248, and 343. All right, so we need to turn stat plots on. You remember how to do that? Go to second y equals. Make plot 1 go to on instead of off. And we might have the bar graph or the histogram selected. Make sure you select scatter plot again. That one. And then you can go to zoom 9. And this is what zoom 9 looks like. Oops, looks like I got something in y equals. Let's clear that out too. Okay, zoom 9. Looks like that. Okay, so let me write down some steps so you have them when you're doing the homework if you need it. We went to second y equals. You hit 1, which was plot 1. And we turned it on. And the other thing was when you saw type, we wanted it to be the scatter plot. So you selected the scatter plot type. And then you always go to zoom 9. That's the stat zoom. So it'll do the scatter plot for you. And just do a quick sketch of what it looks like. So again, this is what I was looking at. Something like that. So based off of our pictures, which scenario does that look most like? Let's say exponential, right? So I'd say exponential is the one we want to use here. Okay, so now that I did that, we want to determine the regression equation for the model we chose in point B, rounding all coefficients to the nearest 100. So this is where I go to stat calc. I just have to choose, I want the exponential one. So it's choice 0, which is EXP REG, exponential regression. So I'm going to go stat, calc, choice 0 is exponential regression, L1, L2 should already be there, go all the way down to calculate, and it gives you the equation, and it gives you the A and B values. And it says round to the nearest hundredth, so it's going to be 15.39 times 1.05 to the x. Don't forget y equals, or whatever variables they give you. They don't specify here, so you can just say y equals 15.39 times 1.05 raised to the x. Right, and then part C, using the equation you created in part B, algebraically determine the speed that would correspond to a stopping distance of 400 feet. So you got to look at your original table. They're giving you a stopping distance. So they're giving you an L2 value. So it's L2 x or y. L2 is always y. So we want 400 feet. I would expect it's going to be higher than 70 miles per hour. So let's see. We're going to do 400. equals 15.39 times 1.05 to the x. Now here's where I love this lesson because it's kind of a review of lots of different things we did this year, algebraically. So I can't just do y1, y2 calc intersect. I've got to solve for x. What's the first thing I would do to try to get x alone here? Yeah, you can't multiply this in, remember, because the 15.39 doesn't have the x on it, but you can get rid of it by dividing. So we divide this by 15.39. Let's see what that is. 400 divided by 15.39 gets me that big number, 25.99 dot 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 equals 1.05 to the x. All right, and then do you remember how to get rid of this 1.05? That was a log. So if you want to get rid of the base of an exponent, you take the log of that base. So if I just do log base 1.05 of the 25.99 number equals log base 1.05 of 1.05 to the x. Do you remember what happens when you do that? Those cancel. So x is alone. And then as long as you have one of those newer calculators, if you do math, alpha, math, you'll get that log base. So log base 1.05 of that big number. Hit enter. 66.77 dot dot dot. It says round to the nearest mile per hour. So x is about 67 miles per hour. Now, if you'll notice, that doesn't totally make sense based on our data, because 67 looks like it would be between 248 and 343. So there could be a couple things going on here. For one thing, we rounded the coefficients. If we didn't round these and use the big long decimals the calculator gave us, I expect this might be bigger than 70. So rounding error can give you a drastically different answer. This is correct for the situation we have, but if this was in the real world, I would recommend not rounding. Okay, let's try the next one. Okay, new scenario. When debris is dropped off a cliff, its height, h, is measured in feet, t, measured in times per second. Determine a regression model that would be a good fit for this data, rounding to the nearest whole number. Okay, so again, I have to go back here, and I want to go to stat edit. We're going to take out L1 and L2. Put this in instead. So we got 0 through 5. Oops. And the corresponding heights. 875, 843, 807, 741, 662, and the last one's 450. All right, now your stat plot should still be set, so we don't have to do this every time. I can go straight to zoom 9, and I've got that shape. Okay, so let's look at that. Something like that. Okay, what shape do you think that could be? Is it exponential again? Potentially. There could be an asymptote up here. So I could see exponential being an option. Which other shape do you think it could be? Maybe logarithmic, if it kind of went the other way. Or it could be quadratic. Remember, quadratics could flip upside down. If it's quadratic, it would look something like this. And if we just took this side of it, well, that looks almost exactly like what I have here. So I would say quadratic probably is the best. So we're going to go to stat, calc, quadreg. Stat, calc, quadreg is choice 5. all the way down to calculate. And it wants you to round it to the nearest whole number. So negative 19x squared plus 18x plus 861. Now the other thing is this one did give you specific variables. They want the time and height. So you really should have h equals negative 19t squared plus 18t plus 861. So as always, watch those variables because that loses you a point for notation. Using the model you create in part A, determine the height of the degree 7 seconds after it has been dropped. Is this interpolation or extrapolation? Well, if I want to determine the height, 7 seconds is a time, so that's t. So I just plug 7 in for t. H equals negative 19 times 7 squared plus 18 times 7 plus 861. And I would like to see that 7 written out like this. So negative 19 times 7 squared plus 18 times 7 plus 861 gets me 56. So that'd be 56 feet. Is that interpolation or extrapolation? Well, 7 is outside the range of data we have, so that's extrapolation. So extrapolation, because x equals 7, is outside given domain. Our domain was 0 to 5 because that's the data we're given. All right, last part for this one, using the model you created in part A, algebraically determine when, to the nearest tenth of a second, the degree will hit the ground. What do you know about the height if it's hitting the ground? The height would be 0. So it's using this equation but plugging 0 in here. So I need to solve 0 equals negative 19t squared plus 18t plus 861. Anyone remember how to solve that? Solve a quadratic. More good review from the year. This is when you have to use potentially quadratic formula, but maybe it factors. Remember what that thing is you should check first? The discriminant, b squared minus 4ac. Let's check this. So b squared minus 4ac is 18 squared minus 4 times negative 19 times 861. Let's see what that number comes out to be. So 18 squared minus 4 times negative 19 times 861. 65,760. What does that tell us? Well, we need to know if this is a perfect square or not. So if I take the square root of that answer, that's not a perfect square because it's a big long decimal. So if it's not a perfect square, what does that tell us? Isn't this great review? You love this. It tells you that it doesn't factor. So if it doesn't factor, use the whole quadratic formula. And quadratic formula was x equals negative b plus or minus the square root b squared minus 4ac all over 2a. Okay, so we can sub all that in. X equals negative 18 plus or minus, we already know this is the square root of 65,760 because we did that part, all over 2 times negative 19. So we're going to have two possible answers. I'm going to use alpha y equals. If you have an old calculator, you got to be a little more careful about how you type this in. If I do negative 18 plus radical 65,760 all over. It's going to be negative 38 on the bottom. I get negative 6.27. Dot, dot, dot. And then the other answer would be if I took that big number and instead put a minus sign there. And the other possibility is 7.22 dot, dot, dot. So if I'm asking when the degree hits the ground, which one of those is going to make sense? You're not going to talk about negative time. That would just have been the answer that would have happened over here. We only want the positive value. So it's going to be, what did it say, round to nearest tenth of a second. So x is about equal to 7.2 seconds. All right, so if you need to solve an equation algebraically, if it's a quadratic, you might need to use that process. All right, last page. Izzy developed a new caffeine drink designed to keep students awake during math class. Her profits during her drink's first year on the market are summarized in the table below. What type of function would be best to model this data? Create a regression equation to model, rounding all values to the nearest thousandth. All right, one more time. We got to go to Stat, Edit. We take out L1 and L2 and put these in. So we got a whole year, so 1 through 12. And then the corresponding profit. She lost money in January. Oops. And then she broke even in February. And then after that, she started making some money. Sometimes it takes a while to catch on. Until June, in month 6, she's back down to 0. And then for a while, in months 7, 8, and 9, she seems to be losing money again. That's too bad. But then in month 10, she's back even. November, she's up to 42. And December was 116, her best month yet. All right, so to figure out what function would best model it, let's go to Zoom 9. And you've got that shape. So just give me a quick sketch of that. So again, to figure out that, we always go Zoom 9. And the graph looks something like this. What type of graph would that be? Go back and look at your options. It's definitely cubic. Okay, now they also want you to do the regression equation right here. So I'm going to go to Stat Calc, cubic reg. I think it's choice 6. Stat Calc, yep, choice 6, cubic reg. And there's no specific variables I need to use this time, so using x and y is fine. Everything's to the nearest thousandth. So we're going to plug in A, B, C, and D in the correct spots. It comes out to be y equals 0.961 x cubed minus 17.238 x squared plus 87.246 x minus 110.020. All right, give a reason why your profits may have decreased between months 6, 7, and 8. So really 7, 8, and 9, I guess. Why would it decrease? Well, it decreased between 6 and 7, went down, then it went up again. So why is it going down here? Well, think about what she's doing. It's a caffeine drink designed to keep students awake during math class. But months 6, 7, and 8, when are those? Those are the summer months. You don't really need to stay awake then anymore. So just the demand went down. This isn't really a math question, it's economics. It's summer months. So there's less need to stay awake in math, or less demand to stay awake in math. Okay, do you think the function you created will model Izzy's profits over the next year, where x is an integer between 13 and 24? So if I kept going into the cubic graph, what's going to happen to this? Is it going to cycle again like this did? No, it's going to just keep growing without bound, which for Izzy would be great, but most likely it's going to follow this kind of ebb and flow again, where it's going to go down in the summer and then go up in the fall. So I would say no. And that's because cubic functions go to infinity as x goes to infinity. That's the end behavior. It's unlikely that Izzy's profits will grow without bound. Again, she would hope it would, but it's unlikely. It'd probably be more periodic, we'd call it, because it repeats at regular intervals. All right, I got one more for you, then we're done. The data below shows the heights of 12 weeping Hagen cherry trees planted in Washington, D.C. Washington, D.C. is known for its cherry tree festival. In relation to the age of the tree, at the time of planting, the trees were 1 year old and were all 6 feet in height, so they all started the same. And now these are the heights of the trees after a certain number of years. So we got to go to L1 and L2. We got 1, 3, 5, 7, 9, and 11. And it looks like the trees are continuing to grow, but they more than doubled in those first couple, and then they don't grow quite as fast. Kind of like humans, except humans stop growing at a certain point. Trees continue to grow. All right, let's check what this looks like. So zoom 9. Okay, there's our scatter plot. So when it says determine an appropriate regression equation, we need to go through the whole analysis of what the graph looks like. It's growing at first and kind of leveling off. What kind of graph grows at first and then levels off? Logarithmic. So I would say this is a logarithmic one. Okay, so we're going to go, that's the most appropriate regression model because of that leveling off. We're going to go to Stat, Calc, LN regression. So Stat, Calc, LN reg is choice 9. And we want to round everything to the nearest hundredth, so it's going to be 6.33 plus 5.98 ln of x. And they don't give you specific variables to use, so we can use x and y. So y equals 6.33 plus 5.98 ln of x. There you go. And based on the equation you created, determine algebraically the age of a tree that's 10 feet in height. So if the height is 10, that's an L2 value. Is that x or y? That's y. So 10 equals 6.33 plus 5.98 ln of x. And we got to solve for x. So what would you do first? Subtract 6.33. So I'm going to do 10 minus 6.33, and I get 3.67. So 3.67 equals 5.98 ln of x. Then what? Yeah, divide by 5.98. They'll probably give us a big long decimal. So don't round until the end. That's important also. So 0.6137 blah, blah, blah equals ln of x. And then this is back to review again. Do you remember what gets rid of ln? Well, ln is a log. It's a log base e. And you have to do that process of exponentiating. You exponentiate by e. So you do that to both sides, cancel out. And then you have e raised to that number. So use that so you're not rounding. And you get 1.847, blah, 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 equals x. We wanted to talk about the age. All the ages are in years here, so let's just say this means, it didn't tell us what to round it to, but it's about 2 years old. All right, that's the end of it. So give the homework a shot, check your answers, and email me if you run into any problems. Good luck.